Yeah, hi, my name's Jim Vollinger, teach at Northfield Mount Herman School, and this video is meant to help kids in my calculus class. Going to try to tie together some concepts about differentiation, integration, and play with some squares and some rectangles. So let's have at it. So first day of the semester, we talked about, you're a little tot, and somebody puts you up against the wall, puts a little mark on the wall, and it says how tall you are, and then a month or two later, you measure it again. And if we want to talk about rates of change, it's the change in height over the change in time. And we get a feeling for a rate, whether it's a growth spurt or not. Right now, I'd be this fellow right here. I'm heading in the negative direction. My height's decreasing. And so those comparisons gives us a feel for rates of change. On calculus, we want to look at those rates of change over smaller intervals. Instantaneous situations. At a moment, how are things changing? So let's look at the easiest function perhaps to understand, y equals x squared. So let's look at y equals x, and then let's talk about how it's changing. And if we want to talk about it in an instant, then we're talking really about the next biggest rectangle possible, which is pretty hard to consider because if you changed the dimension by 0.01, you could also change it by 0.001, and by 0.0, you could do that forever. So really, it's kind of an abstruse concept. But let me draw some sort of change here, and let's give it some symbols. So let's say, so you can see it. All right? And let's call this change dx. Let's cut right to the chase. A little change in x, a little difference in x. And so we have from here to here is still x, from here to here is still x, and then this would be a dx times dx. And it looks like we can measure our change. And we'll call this y. And so this is our change in y right here. And so our change in y is equal to x dx, x times dx, plus another x times dx, that's a rectangle, and dx times dx, which is squared. And if we group these terms, then we get 2y equals 2x dx. And we'll talk about this in a second. Let's talk about it right now. Let's talk about a 3 by 3 square, x and x squared. Let's talk about a 3 by 3, gets us 9 units of area. And let's talk about the limiting process of making this head to 0. So let's talk about 3.01. Let's square it. If you square that from calculus, we know it's going to be 9.0601. Yeah, I get the right number of decimals. And if I made it 3.001, then it would have been 9.006001. And if I did 3.0001, you probably anticipate, everything in math is patterns, 00060001. And we can talk about this as our first x. We can talk about this as our first y. In each of these, we can consider a second x. Each situation. Let's just consider a second y, a second y, a second y. So if we use our analogy of measuring change, then we can look at, let's just look at the easiest one. We've got 9.0601 minus 9. We've got 9.0601 minus 9 over 3.01, 3.01 minus 3. And I think we can see 0.01, 0.0601, and approximately 6 units of change. Oh, yeah, that is 2 times x if it was a 3 by 3. Okay, so where do I want to go with that is, oh yeah, so let's write down, let's try to capture symbolically what we just did here. What we basically did is we looked at a limit because dx times dx in this case, dx times dx would have been 0.0004567 8 decimal places, and I think we can say that that's so negligible. It's the cusp, it's the corner of the square. We're gonna just ignore that as part of the accumulation of area. So what did we do? Well, we looked at the limit as x approaches 3. That's what we really did. These x values are approaching 3, and we took a generic x squared, in our case 9.0601, and we subtracted 9, which was our original area, and we let our x's go to 3. And we can do that limit using algebra. So we can look at that limit as x approaches 3 of x plus 3, x minus 3, x minus 3, which is equal to x plus 3. Right? The limit as x goes to 3, we can see is 6. And we've kind of proven that numerically. We've kind of proven it geometrically. And now we're using a limit to show it as well, which is more of a formal definition of a derivative. We'll be talking about that quite a bit this semester. So now let's look at, so that's just a quick example of taking a derivative. So we'll be taking derivatives of a variety of functions this semester using the same technique, but we're also going to do integration. And I want to look at how this relates to integration now, and then take a little poetic license with the diagrams and have some fun. All right, so let's take our, let's use a unit square here. Bumpity, bumpity, bumpity. Okay, close enough. That's a pretty good square. All right, and let's think of this as a 1 by 1 square. 1 by 1, and let's go to a 2 by 2. Let's go to a 2 by 2, 2 by 2 square. All right, pretty quickly done. All right, and so now we have 1 by 1, 1 unit of area, and 2 by 2, 4 units of area. And I think that our net change is going to be 4 minus 1 over 2 minus 1. Right, the dimensional change, the area change. And we can see that that indeed is 3 units of new area. But how would we use the diagrams that we had over here to symbolically do this from a kind of a different perspective? Well, we'd do some layering. We would just layer the square, each layer slightly more area than the previous one, but notice my dx in this case is actually the width of the marker, which is independent. That's the same each time. And so what am I doing? I'm slowly but surely filling in 3 units of area, which is the net change. That's the net change from a 1 by 1 to a 2 by 2 situation. So let's slow it down, slow motion. X dx, x dx, x dx, x dx. Seems like I'm adding 2x dx from 1 to 2. And this symbol looks like an S, the integral symbol. Right? You can think of it as summation. You can think of it as adding up the area under a curve. What curve? Well, if this was a door hinge, right, and each of these is an x, and each of these is an x, and I turn that upwards, then I've got x plus x, which is 2x, and so I have a function. And I'm really measuring from 1 to 2. And if I went back to 1, boom, x dx, whatever that distance is, I probably should do this better. Whatever that distance is, which in this case is 2 units high, so let's actually do it. 1, 2, there, that's better. That's a better graph of, close enough. All right, so I would get 1 unit, then the next one, so let's go back here. Then the next one would be here, and then the next one, so on and so forth, until I filled up from 1 to 2, where each of these widths I'm calling dx, and each of these heights I'm calling 2x. Well, that's a trapezoid. I think we can see what the area of a trapezoid is. We've got the function 2x, so the altitude on the left is 2, the altitude on the right is 4, and the formula for trapezoid is width divided by 2. So 2 minus 1 over 2 times the altitude on the left plus the altitude on the right, the average of the left and right-hand rectangles. Lo and behold, half of 6 gets us 3. 3 units of area. So this gets me 3 units. And what did this do? This thing measured the change in area of x squared from 1 to 2. And the fundamental theorem says take the value evaluated at the right-hand point, which is 4, 2 squared is 4, minus the left-hand value, squared, in this case 1, and there's your fundamental theorem. So let's continue with this drawing, and let's change it a little bit, have a little fun with it. So we're going to come over here, I guess, Joe. Buddy Joe helping me film this. So I don't know where you want to be, but we'll do it here. Okay. So we started with this square. We talked about the area changing. Right here, that area changing. That area changes by the area. The change in area is 2x dx. The change in the area. So what if we were to draw this rectangle differently? What if we said, okay, let's fix the dimension on the left, and let's just call it a unit of 1. Then to capture x squared, the base has to be x squared. And to capture the rate of change, this rate of change here has to be the same as that. But I'm not changing this dimension. So therefore, that has to equal 2x dx. And let's have a little fun with the commutative property of multiplication and change this to dx 2x. That also captures the rate of change. And that actually helps us quite a bit because this could become any function now. And if we work with this model, then we've got ourselves 2x, which is that graph we did just a second ago, which was dx is change on the x-axis. 2x is a function. And now we have this layering process, which matches up with what was drawn over there before. Layer, 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 layer. So why would this become helpful? Because it allows us to change this function to any function we want. So let's say that instead of x squared, let's take some function. Let's just call it f of x. And let's just say that we knew what this was. Let's say we take this, and let's call it cosine function, and a little change in x. Let's just play with that for a second. I don't have my eraser, so I'll use this for now. All right, so I'm drawing a new graph. I'm drawing the cosine graph. And let's start from 0. Take a little liberty here. So there's one period of the cosine function. And dx is a width, cosine's a height. And so there, I don't want to see how this accumulates. I just want to get a little rough sketch. So there's positive accumulation because I'm x2 minus x1, x2 minus x1. In this case, my second x is bigger than my first, so that's positive. So my widths are positive. Heights are certainly positive. So I've accumulated a little bit of positive area, or right there. And that means that from 0, I'm going up. And then the next rectangle, because the curve is coming down, is actually slightly less than the first one. So I'm still going up, just not quite as much. And each time I do this, I accumulate area in a decreasing way. Positive area in a decreasing way until I get to pi over 2. And once I get to pi over 2, well, let's accumulate that. Let's take a gander at how much that is. So cosine is 1. Pi over 2 is roughly 1.57. 3.14 divided by 2. So we could get a little estimate using a rectangle. I think algebra 1 should be called what we can do with rectangles. And so if you were to estimate that, it kind of looks like 1 unit of area. Right? 1.57 times 1 is the whole rectangle. It looks like 1. So it looks like we've accumulated 1 unit of area when we get to pi over 2. 1 unit of area. Maybe you're already anticipating what's happening here. Sure looks like when we get to pi, we probably, I should draw my accumulation better. X dx, x, right? Cosine x dx, cosine x dx. Sure looks like this is still moving in the positive width direction, but my heights are negative. So I'm accumulating negative amounts, and they seem to be symmetric. this positive and this negative. Probably brings me right back to 0 at pi. And then accumulating negative area, less and less of it though, which takes me to -1 and then back up to where I started from. And so it looks like the area under the cosine curve produces the sine curve, which is kind of interesting. How about if we drew this slightly differently? So let's draw this, let's go back to x squared, but let's have a constant, height of 1. Let's let that be just a height of 1. Then I'm on the x squared axis. I'm on the x squared axis. And so let's talk about how things accumulate under a curve of 1. Let's go from 0 to x squared. Under a curve whose height is 1. Let's just think about that for a second. Let's talk about how area changes. Well, from 0 to 0, there's no area accumulation. But let's actually let x equal 3. And let's talk about how things are changing. All right, let's let x equal 3, like we did over there. And then let's look at 3.01. Let's look at 3.01. That'll be interesting. All right. So when x is 3, 3 squared is actually 9. So we're not at 3 anymore. We're not in Kansas. When x is 3.01, 3.01 squared is actually 9.06. And 9.06 to 9 is 0.06 is the width. And the height is still 1. And how much did we change our x's by? So this is 0.06 units of area. And we changed by 0.01. Now we're back to a 6-to-1 ratio. So now we're talking chain rule, which is something we're going to study later in the term in a deeper way than this. I'm just trying to put a few thoughts in your head. All right, so that ties a few things together. Integration and differentiation are brother and sister. They're inverse operations. And just like addition and subtraction, they're linked. And we're going to talk about that link through the entire semester. All right, so just a few things to think about, and we'll be discussing them in class as we move along. All right, thank you.